Okay, this week I have 5 problems here. The first three I think are not too bad, but then I would say the last two require a bit more work. So let's get started. First problem, it's hopefully an easy warm-up question. You're basically given two numbers, x and y. X is the number of sweet jars, and y is the number of sour jars. Um, if they're both zero, then that's the end of input. And then you have to check, right? If they're more sour than sweet, it's left behind. If they're more sweet than sour, then he'll go to the convention. If it's the same, then his friends are undecided. And then there's this last one that if he has exactly 13, then they'll never speak to him again. And the important thing is to realize that you need to check um, the exactly 13 before you check the other ones, because if you have exactly 13, you want to say they never speak to him again, even though it may be more or x may be more or less than y. So that's really the only other thing is to make sure that you type this out exactly the way it is, including the last period and uppercase, lowercase, and all that stuff. Um, and that's it. Okay, so there's not too much more for me to say, so I'll just go straight to my submission. Um, so here I have a loop that calls solve. Solve will return true if it's not the last case, and false if it's 0, 0. So it reads in x and y. In this case, x and y are small, less than 1,000. So no need to worry about long, and so on. Just use normal int is good enough. If x and y are both 0, then return false. Otherwise, you do the if then else check. The main thing again is to check that x plus y is equals to 13 first. And then if it's bigger than y, equals to y, less than y, basically all 4 cases. Okay, that's not too much more I want to say about this. It's hopefully it's fairly straightforward. So let's get to the second problem. Okay, second problem is a little bit more interesting. You have a disk with a plane in the center 0, 0 and some radius r. R is at most 1 million. And oops. And you want to find a point that it's outside the circle. So distance from is strictly larger than r. And it's also an integer point, x and y. And you want the x and y coordinates of a convenient building location that is closest to this district. Okay, so you have x and y. You have a circle. Try to draw a circle as best as I can of radius r. You have integer points. So these are the integer points. And you want to choose an integer point that is outside the circle. But out of all the ones that are outside the circle, you want the one that is closest to the circle. Okay, and so on. Now, the first thing to realize is that you only need to worry about points that are in the first quadrant. Because if a solution is, let's say, here, if you can find a solution here, well, you can reflect it and get the same solution here. Okay, so there's no need to look for any um, answers outside of the first quadrant. So immediately we can say that x and y is greater than 0. R, it's at most a million. You want something that's just outside, so you know that you never have to look at x and y that are bigger than 10 to the 10 to the 6 plus 1. You never have to worry about more than 1,000,001, because if it's 1,000,002, well, there would be a point that's closer. Okay, just by reducing the x or y coordinate that's 1,000,002 to 1,000,001, that would be a closer point. Okay, so we can say, well, okay, if x and y are between 0 and 1,000,000, then we can try perhaps all x and all y's that are right a double loop, let's loop for x being 0 to 1,000,001, y being 0 to 1,000,001, compute the distance, pick the one that has the minimum distance. That doesn't work because in that case, the loop will be 1,000,000 square, which is 10 to the 12. That's way too much. That's going to take too long to run. So now you have to be a little bit more careful, more clever, I guess. And the idea is to make use of the fact that you have a circle, and you know that in this circle, x squared plus y squared, it's equal to r squared. So if you know what x is, or y, either one, if you know what is x, you would also know what is y. Okay, so maybe this doesn't pass through. Okay, whether it passes through this exactly, we don't know. So let's actually just make it not pass through exactly. Most likely it doesn't pass through exactly. Sometimes it does. Okay. We want to know where is this point on the circle at the certain x coordinate. Well, you have to remember then that this may not be an integer, y may not be an integer, but if you know what x is, so given x, then y is equals to r squared minus x squared square root. Okay, which may be not an integer. So what do we do if we want to find a point that's just outside? We round it up with ceiling. Now there is a problem perhaps that you can say, well, if you do r squared minus x squared, and let's say this is, I don't know, 5 squared minus 4 squared. So this Pythagoras tripled. 5 squared is 25, 4 squared is 16, so this is 9. And then when you take the square root, it might be, if you're lucky, you get exactly 3. And you round up, it's 3. Or maybe it's your sums of round over and you get 2.9, you round up, and then you say, uh-oh, that's not quite right. Because we want to get something that's just outside. Okay, so we have to worry about that. But if you just round it, you might not be outside. We can just check. Are you really outside? Or here's another trick, I guess. So you can say, well, I know r squared minus x squared. I try to take the square root and round it up, right? And now you can pick that number and say, this is an integer now. All of these things are integers. Well, okay, I shouldn't use ints because they're not ints. I'll get to that. They're integers, no rounding error. So now I can take y squared, r squared, and x minus x squared. All of these are integer values. And I can compare. Is y squared bigger than r squared minus x squared? And if not, if you run into this problem where maybe r squared minus x squared, picking a square root, it's a little bit too small because of round off errors, so that when you round it up, it gives you the wrong answer. Well, add 1. So if y squared is not bigger than r squared minus x squared because of round off errors, then just add 1 to y. And then you're okay. You're guaranteed to be just outside. So basically, what we're going to do is we're going to loop through all the possible values of x from 0 to r plus 1, which can be up to 1,000,000 plus 1. For each x value, we figure out where y should be. And once we know where y should be, we can then compute the distance of that point, which is x squared plus y squared square root. But we don't do the square root because we don't want to do round off errors. So we just compute the square distance and pick the point that has the minimum square distance. Because we know, given a particular value of x, how to get y in constant time, we just have to loop through the 1,000,000 values of x, and now we're okay in terms of time. The only other thing that you have to worry about is, because these things are up to 1,000,000, and you're going to be computing squares of 1,000,000, you need to use 64-bit integers for this to work. Otherwise, you'll get overflow. So you need to make sure that you use 64-bit integers in all your calculations. Okay, so um, those are all the tricks for this problem. So let me just show you my submission. Okay, in this case, there's only one case. So first, I type def long to LL, so I don't have to type long all the time. So LL is my 64-bit integers. I read in the radius. R2 is basically R squared. And then I basically figure out, I have to remember what is the best X and best Y. Best X, well, if you just make X to be R plus 1, then Y is 0. So if you just put it on the X-axis, then the best Y is 0, and the best X is just outside the radius. And the distance, the best distance squared is this, okay, R plus 1 squared. Then for each value of X, I guess I actually can stop before R plus 1 because I already set this here, but it doesn't really matter. Then I compute Y2. So Y squared is R squared minus X squared. Then I do square roots of Y2, the square root of Y squared, and take the ceiling. And then if I squared and then end up being the same, that means I must have been screwed up by my round of errors. So I just add 1 to Y, just in case. And this will make sure that you don't get screwed up by round of errors. So always try to avoid square roots if you can. Try to avoid floating point numbers. But if you can't, then you can do kind of a post after you do your calculation check to see if the answer makes sense and adjust if necessary. Now that you have your X and Y, that's your candidate point. So you compute the distance squared. If the distance squared is better than what you had before, then save the new point as the best you had before. And then at the end, you print out the best point that you found. So this loop, it's only 1,000,001 step. So it's fairly fast. If you want, I mean, if you really want, you can even say, I can cut this in half. I don't have to do all of the search because if you just look at the first quadrant and you draw the 45-degree angle, whatever point you find here, you reflect it, will be found here. So you really only have to check for all the points, I guess all the X from this point to this point. But then you have to figure out where exactly this point is and so on. It's a bit more of a pain. So even if to try all the X's good enough. So let's not worry about it too much. Okay, so this is the second problem. This district, mainly, I would say that the algorithm itself should not be too bad, but then you have to deal with the floating point issues carefully. And then when you try to avoid the floating point issues, you're going to end up with the 64-bit integers. So all of that you have to take care of. And it's some sort of a matter of making sure that you take care of those little details carefully. Okay. Very, I don't know what language this is, metadata. Croatian, I guess it must be Croatian. Okay, it doesn't really matter what that means to us, but basically you're given a string, right? So dog, A, or some other string like ABCD, and you're supposed to draw it out in 5 lines. And then you have these diamond shape that are either pound sign or star signs. Every third one is a star, and then star overrides the pound signs. And that's basically it. So there are a bunch of things you have to worry about. I guess first you have to figure out how big this output is. It's always 5 lines, but how many columns? And the number of columns is basically every single character you get gives you 4 columns because there's an overlap here. So not 5, but every letter that you get gives you 4 more columns. And then at the end, you have 1 more to close it up. Okay, so it's basically 4 times the number of characters plus 1. And then you have to figure out how you put these things, right? So you have to kind of realize that the first character is at position 2. Second character is 5 more, 1, 2, 4 more of that. So you add 4 to everything. And then the pound signs, you have to figure out exactly where it is. The easiest way that I decided to do this was to write a function that will take the coordinate at the upper left corner of that block. So you figure out the upper left corner is 0, 0 for the first one, 4, row 0, column 4, row 0, column 8, plus 8, plus 4 every time. And then from that origin, the first line is already plus 2, second line is plus 1 and plus 3, and so on and so forth. So I write a function that will draw this diamond and the letter given the origin, and I just call this repeatedly in a loop. Only other thing that you have to worry about is that you don't want the pound sign to overwrite the star sign. So if you just if you just call this function one character at a time, then calling in a fourth letter would overwrite this star, which you don't want. So you basically want to call all the ones that are pound sign first, and then you call the one that is stars last. That will basically eliminate. They will have the stars overriding the pound. So anyway, that's kind of it. It's not that it's hard, but it's perhaps takes some experience to write this in a more concise way. So here it is. I read in the string. The length of this grid is actually, as I said, 4 times the length of the string plus 1. And then I create a vector of string as my output. There are 5 of them. Each one, it consists of a bunch of dots. So this is a constructor that constructs a string, each of this length filled with dots. And then I'm going to go through the string, and for each one, so I check if it is not every third letter, so 0, 1, 2, 3, 4, 5. So every third one is when the index divided by 3 has remainder 2. So if it's not every third one, then I call my function with a pound. Otherwise, then I go through the loop again, and if it's every third one, I call my function with a star. And my function takes the character that you want to put in the center, pick the column that you want to start at, the grid that you're trying to write to, so it's passed by reference, and then whatever mark you're using for the diamond. And then I just basically wrote this. The first line, it's always column plus 2. Second line is always column plus 1 and plus 3. Middle is always column and column plus 4, and so on. And then the second line, sorry, line number 2, column plus 2 is always the character that you're trying to write. Okay, so again, this is maybe you can say is a little bit messy. It's not exactly hard, but if you want to do it in a less messy way, then of course it takes a little bit of experience and practice to be able to write code that are a little bit more succinct. Okay. I actually want to skip this one. If you actually look at my, if you have looked at the standings, you see that it took me 10 tries to do it, and then I'll kind of explain why when we look at the problem. It's basically the same silly bug that I didn't see for 9 times, and then the 10 times I finally saw it. Anyway, okay, so this one, it's a little bit more algorithmically challenging, I guess, but it's if you have never seen this before, then hopefully it will be educational. Okay, some days the university campus gets very wet. Other days it can get very cold, although many times it is pleasant to be outside. There are days when we would prefer to stay indoors. Luckily, the campus designers have gradually connected various buildings with tunnels and bridges. Sometimes these connections are built when the building is built, but it may also be possible at them afterwards. Unfortunately, sometimes it's not possible to travel between two buildings without going outside because the system of bridges and tunnels is not complete. You'd like to write a program to help a newcomer determine how many buildings can be reached from a newly constructed tunnel. Okay, first line of input contains the non-negative integer n, the total number of bridges or new tunnels built. It's no more than 100,000. We assume that all of these buildings have been built ahead of time, but at the beginning of the test case, no bridges or tunnels have been built yet. The rest of the test case consists of n lines giving the history of the bridges or tunnels in the order in which they are built. Each of these lines contains the names of two buildings being connected, separated by space. Each building named is a sequence of up to 6 upper and lowercase letters, and building names are case sensitive. So whenever a bridge is built, a tunnel is built, print a line containing one integer, the number of buildings that can be reached from that bridge without going outside. So first MC and DC are connected. So those are the only two buildings that are connected. So you can reach two. Then DC and Eng are connected. And because DC was connected to MC, now you can reach three buildings. And then this M3 is connected to MC, and because everything else was connected before, so now you can reach four. So this, it's what we call, well, so okay, so there are two things. So first, you have a graph, and we're talking about connectivity or connected components problem. Okay, so that's the first part. You have buildings that are nodes in a graph, right? So you have buildings that are node in a graph, and then you know that some are connected, maybe these two are connected. And if you want to know how many there are, you do some sort of connected component analysis that we talked about last time. For example, depth first search, breadth first search, and so on. And you discover this connect component has three things, and this connect component has two things. Okay. The problem is that you are not just given the buildings and the bridges, and that's it. This is what is called dynamic connectivity or connected components problem, because these bridges, these edges in the graph, are added dynamically. And every time you add an edge, the graph changes and you want to answer, right? So maybe this is now connected, and now you have to answer two. Then maybe this is connected, you have to answer two. And then when this is connected, you have to answer four. Okay, so every time the graph changes, right, you have to answer something. So you don't have just a static graph that never changes, you answer a bunch of questions. The graph is changing after every time you ask a question or before you answer a question. So the fact that it's dynamic means that you can't just use the standard algorithms. Well, okay, let me backtrack. If you were to use the standard algorithms like depth first search and so on, you're going to have to modify your graph and do the depth first search every time a new edge is added. It will give you the right answer, but it will take too long because it's a lot of work. Moreover, if you realize that all of these are one component, and then you have another component, and then you connect them, you would have to redo all the work if you start the DFS again. So we want to be able to figure out a way to basically reuse the work and not have to start from scratch. And luckily, there is a data structure that you may have heard of. I don't know if you have seen, but you can look it up, or it's called, there are many names for it. Some people call it dynamic equivalence relations. Things that are in the same group are equivalent to each other. Some people call it disjoint set data structures, and some people call it union-find data structure. Okay, and if you go to my code library, and go to here, it is in union find. So here there's a class here that you can use, and you initialize it when you construct this. You have to say how many objects do you want to keep track of. So in this case, how many buildings. And then at the beginning, all of them are not connected. So union find initially, everybody is separate. Then you can merge two things. So if the labels are between 0 and n-1. So if you're building 1 and 5 decide to merge, then you can call merge. Merge will return true or false if you merge two things that were not merged before, it will return true. If you try to merge things that were already merged before, it will return false. But in any case, it will merge them. But it doesn't just connect X and Y, it also connects all the things that were connected to X with all the things that were connected to Y. Find X will give you a label for X. So everybody will have a label, and the label is returned by find. And if two things have the same label, then they are connected. And if two things have different labels, they are not connected. That's how unit find appears to the outside world. Exactly how it works inside, that we could talk about in some other day. The important thing is that this allows us to dynamically keep track of relationships and things as things are merged. And each operation that you call, you can assume that it's basically constant time. It doesn't matter if you have a billion things that you're keeping track of, it takes basically constant time. Now, I say basically because it's actually not. If you really want to look at the complexity, you will run across something that looks a bit strange. If you look it up online, it's called an inverse Ackermann function. And it's actually not constant time. It's a function that grows as n grows, but this function grows so slowly that even if n is like the number of atoms in the universe, the function value is only like 5 or 6. Okay, so basically you can almost pretend that it's constant time in practice. In other words, it's just fast. Another thing that I lied about is that it is not true that every single operation find and merge is fast. It is possible that a single find or a single merge can be very slow with a billion things. However, if you do a bunch of them, if you have to do a slow operation once, you will not have to do a slow operation very often again. So this is much more advanced, complex analysis that it's called amortized analysis, probably which not taught until at least the 4th year. But anyway, in practice, the only thing that you have to know is that it's essentially constant time, even though it's a bit of a lie. So anyway, the idea is to make use of this data structure to keep track of who is connected to who. However, the union find data structure that I have that you can download and use doesn't keep track of the size of the component, which is what you want. So what we're going to do is we're going to actually keep track of the size in another array that's indexed by the labels of the components. And then if we keep track of the size that way, then we can print the answer. And the final thing is that if you want to use the union find data structure that I have, you need to know how many buildings there are in the beginning, and you need to convert these names into 0 to n-1. So how do you convert these names? Well, you use a map of string to integer. Every time you see a new name, you check, have I seen it before? If I've seen it before, I return the index. Otherwise, I store it into the table and give it a new index. Okay, so you have a table that translates building names into numbers. But how many buildings do you know? How many buildings do you have? That's a little bit tricky because unless you read all of these things build your table and then go back a second pass, you might not know exactly how many buildings there are. But we don't need to know exactly how many buildings there are. We just need to know, have an upper limit. If we have, if we have 10 buildings and we allocate 30, well, we just don't use the 20 spot. And here we can use this clue. We know that there's 3 bridges or tunnels built. Each bridge or tunnel can give you 2 different names. Now, some of them are not going to be unique, but in the worst case, if every single bridge and tunnel connect 2 buildings that you have never seen before, then the most number of buildings you can ever see is 6. Okay, because there are only 6 names here. So in other words, if you know how many edges you're going to have, 2 times n, it's going to be the maximum possible number of buildings that you're going to see. So we can make use of that in our code. So let's look at the code. The first bit is just copy and paste it. I didn't do any changes. So this is just up to here, just copy and paste the union fine. And then I have a map that take a string to an integer, what I call ID. So this gives me from the name of the building to an integer. And the way I do it here is I write a function called find ID. You give me the name, I give you an ID. So the first thing I do is I ask. So this is a way in C++ container, I take the name of the container dot find with the key. It's going to return an iterator that points to the object, points to the entry that contains this key. Or if it's not found, it's going to return the end of the container. So in C++, in any container, if you try to find something and it returns an iterator that points to the end, remember that the end is actually one element past the end is the imaginary position that doesn't exist. When you see that, it means it's not found. So what do? I figure out what is the new ID, which is the size of the current size of the container. So if current size is 0, that means I have nothing in there, then I want to use 0 as my new ID. If the current size is 10, that means up to now, the IDs are 0 to 9. So 10 is my new ID. And then I just store it into the map. I store it into the map. And then I make use of the property that the assignment operator returns the value it was assigned to and just return it in the same time. Okay. Otherwise, if it's not in this branch, that means it's already in the map. So I just return it. Okay, now I want to write something. This is extremely subtle. Here I wrote it in 2 lines like this. So if ID is a map and the current size, it's, let's say I have 10 elements, then the valid indices up till now are 0 to 9. So new ID is now 10. And when I add the new name into the map, the new ID, so the new entry has ID 10, which is what I want because 10 is the first unused index. Okay, why am I making such a big deal out of this? Because you could have easily written something like this. Okay, so why did I take this ID.size, assign it to new ID, and then assign the new ID into the next in this 2-step process? And why don't I just write it in 1 line like this? Right? So you say the same thing, right? ID has size 10. So ID.size is 10. You assign it to here. What's the big deal? Why did I break it up in 2 lines? And the very important things. This is something extremely important in C++. When you have an expression, so normally when you have, let's say, x is equal to f1 of y plus f2 of z, right? How do you compute X, well, you call F1 with Y, call F2 with Z, whatever answer comes back, add them together, you put in X. Okay, again, why am I making a big deal out of this? The question is F1 going to be called first, or is F2 going to be called first? Normally, you don't care. If F1 and F2 have no side effects, meaning, for example, you don't change global variables or use global variables, then it doesn't actually matter. But if F1 and F2 changes some global variables and make use of them in the computation, then it matters a lot whether F1 is called first or F2 is called first. And in C++, the order that you call these F1 and F2 in an expression like this, it's unspecified. So the standard actually says the compiler is free to choose whichever order it wants if it's more whichever one is convenient. Okay, why is one more convenient than the other? Maybe you were doing things with Z first before the last line, so you still have Z in the cache in the CPU or in the register, so you don't have to reload stuff by calling F2 first. Whereas if you call F1, you might have to bring Y in. So maybe the CPU the compiler decide to call F2 first. And so in C++, it is completely unspecified whether you do F1 first or F2 first. And any code that make use of a specific order, it's what we call ill-defined. We don't know what may actually happen. When you run it on one machine with one compiler or with different settings, it might work one way, and then in the other way, in another setting, it might work in some other way. Okay, so this is very important. Now, why is this important here? Clearly, this is a function call. I call the member function size. But you might also remember that in a map, a square bracket, it's a function operator square bracket, which will go in, and if the key is not there, it will create an entry. So if you assume that you call this one first, look at the old size, and then you call this one on the left-hand side of the assignment, and then assign, then that's what you get. That's the behavior that you want. But there's no guarantee that this is the actual order. It may decide to call the left-hand side first, which would then change the size to 11 already. And then when it calls this one, it will return 11, and it will give the new ID 11 instead of 10. So you skip 10. And basically every time you skip a number. And that is the problem, because if you assume that the number of possible buildings is 2 times n, and you really use exactly union find with 2n like this, then you eventually go out of bounds. Okay, because you're skipping every second one. Okay, so this is a very, how do I say, very subtle point, but writing code this way instead of trying to combine it one line, there's a lot of little detail on why this one is correct and writing it just in one line is not. And that, it's was some of the peculiarity of C++. Anyhow, okay, so this function, after all of that, it's a function that take a string building name and return a unique ID. Okay, so here we are. We read in n, which is the number of edges. Union find is initialized at 2 times n, because there are at most 2 times n buildings. And then I have an array, a vector, of 2 times n entries that keeps track of the size of the component. and it all initialized to 1. Everybody's by themselves at the beginning. Everybody of size 1. For each edge, I read in the 2 building names. I call my function find ID to give me the ID of the 2 buildings. So from now on, I will only work on the IDs. I will look at the size of the 2 chunks. Okay, so union find ID1, that will give me the label of the first thing. And this will give me the label of the second building. And I look up the size of the 2 chunks. Then I merge. I call merge of ID1 and ID2. And if it's true, that means I actually connected something that were not connected before. And that means I need to update the size. If it's false, that means that whatever I try to connect, they were already connected. So there's nothing to update in terms of the size of the chunks. So UF find ID1, that's the label of the new chunk. So after the merge, if it's really merged, UF.find ID1 and UF.find ID2 will have the same label, and it will be it could be a different label than what the label before. So I have to call find again. And the size of it, it's now size 1 plus size 2. Now, I don't have to update both of them because both of them would have merged to the same ID. And then, whether I merge or not for real, I just print out the size of the chunk corresponding to ID1. Yeah, I can do ID2 as well. They are the same thing. So here, basically every time that you have this dynamic relationship between things where everything at the beginning it's completely disconnected, and then at every step things gets connected, it's most like a union find. Union find will only work if the dynamic operation after each step is to merge things. And when you merge, not only do you merge the 2 things that you merge, but also things that are indirectly connected to the 2 things. Okay, so if that's the criteria that in the problem, then you can use union find. If your problem also allows edges to be deleted at some point, then this doesn't work. Okay, so you have to try to do something else, which probably much more complicated, so we won't talk about it. Okay, last problem, university zoning. Okay, there's a lot of things to read, but basically the idea is that you have a bunch of faculties. Okay, there are a bunch of faculties. In this case, there are 2 faculties. Each faculty is given a bunch of squares in a grid, and you number these faculties. You number these cells within each faculty. You number them from top left, 1 row at a time. So this is 1, 2, 3, 4. Right. So 1. Oops. Maybe I need to use a different color. It's the green. This is 1, 2, 3, 4, and then 1, 2, 3. So order by rows, and then if they're the same row, order by column. And then you have a bunch of students, these numbers, 1, 2, 3, these are where the students are. And you want to move them to the position. So 2 needs to move, so it takes 1 step. You can only move up, down, left, right. And then 4 and 5 are already in position. And so basically you have to, given these initial configurations of each faculty, all the students, you want to move them to the right places and count how many steps they all take in total. But they're a little bit more involved because for each faculty, you don't need all of them to be in the right spot. There's a t value for each one, and it's saying that each faculty must have at least t people that are in the right place. Compliance target is met if at least t students found in their assigned cells. If So if you have 10 students, but T is only 4, you just need 4 people to get into the right place. It doesn't have to be in order. Basically, you want to get the closest one. Okay. And then it also have this other thing that is G, which says that only a certain number of faculties needs to be in compliance. So some faculty you just don't care at all. So basically what you have to do, it's for each faculty, you have to figure out how many steps the students have to move to bring them into compliance. And then you pick out the best G faculties, and the rest that takes a lot of steps to make into compliance, you don't care. And then for each faculty, you pick basically again, you pick out the best students, the best T students to get them into position, and the rest you don't care. Okay, so let me kind of this. Okay, I'm not gonna. I have so yeah, I have 10 submissions, but I have some accepted. So where's the first one that got accepted? Because I was trying different things, trying to figure exactly what went wrong. Um, where's my code? So let me show you my code. Actually, I think the last one is the one that I want to show. So basically, the problem was that I made a mistake, then I I start changing stuff and trying to figure out what's going on, and then didn't work. It didn't work, and then at some point it all of a sudden works, and then I had to try to figure out exactly which change um, made it work. Okay, so um, there's a lot of code here, but basically I'll just ask you if you want, you can go and look at my code on GitHub if you want, and see how I do it. But I want to kind of go through um, an explanation of what's going on. Okay, so the first thing that I have to do is I have these faculties. I have a bunch of faculties, and then I'm just going to have a data structure of faculties. And each faculty would have a bunch of cells. The cells are going to be given in rows and column value. Row 1, column 1, row 2, column 2, and so on. And I want to assign them numbers, right? If I have, let's say, this one, this one, this one, this one, and so on, then it's sorted by rows. And then if there are ties, you sort by columns. What I'm going to do is I'm going to actually store these things as STL pair of integers, which, by the way, then the row and column can be up to 1,000,000. So to make things, because I'm going to later on have calculations of coordinates, I'm going to actually just make them long. So um, I'm going to make them 64-bit integers. So just say LL. So pair of longs to store these coordinates. And when I sort them, automatically it will sort things according to the first coordinate, which in this case is rows, right? And then if there's ties, it will be sorted by columns, by second component. So I'm just, for each record, I'm just going to have a vector of pairs of coordinates, and then I'm just going to sort them. That's my faculty. So here, faculty is vector of pairs of integers, but where pair of integers is actually longs. And I have 100 faculties, so I have an array of these vectors. When I read the faculty, I read in how many, for each faculty, I read in how many pairs are coming. I put it into the vector, and I sort the faculty. Okay, so I have these locations in the right order. Then I'm going to have a bunch of students, and the students have student IDs, and the lowest ones are the ones that, so you want to sort them by student ID, and then you have to sort them into the right faculty because each faculty has its own. So I have another array, a vector called nrow for each faculty, which is just a bunch of students. And student objects, which has row and column again, and then the ID would, so the row and column, I think, did I use a pair or just, okay, I just use row and column. D is the student ID, and then F is which faculty they're in, and then I have a sort. Oh, because I'm using zero base, so I just, whatever number I get, 1 to 100, I subtract 1. And then I have an operator to sort things based on the student ID. So I read all the students, I sort, I call s.read to read it, and I sort them into the right faculty list. So nrow, where's nrow? Nrow is a vector of students. Again, there's index by 100, index by the faculty. And then I read this threshold of compliance target for each faculty. So to process the faculty, what do? I sort the enrolled students for that faculty. So now I have all these students that are sorted by ID. So this one go to this spot, this one go to this spot, and so on. And I just basically march along, and for each one, I figure out the distance they have to step to get. So I have a distance array. I figure out how many steps they have to take to get to the right place. So maybe this one takes 4 steps, this one takes 2 steps, maybe this one's already there, and so on. Now, how do I compute this? I have the location I want to go to. So let's call it this destination. And then I have the starting position where the student is. Then how many steps it takes if you can only go left, up, down, left, right. It's what is called a Manhattan distance, which is the absolute value of the difference in row plus the absolute value of the distance in column. So this is sometimes called a Manhattan distance. Here's another thing that you probably want to be familiar with. And so you can have this distance array for each student, how many steps did it take? And if you need a certain number of people in compliance, let's say you need 5 people in compliance, you want to pick the 5 smallest one. Some might be 0. If you have something that's like 100 steps, you don't want to ever use them if you can't avoid it. So what you do now is you sort them from smallest to largest, and then pick the first 5 spots, or first T spots, whatever the smallest one, you add them up, and that's the number of steps you need to take for this faculty to be put into compliance. So that's what I'm doing here. I have a vector of distances. I loop through all the people that are enrolled. I grab the students, I grab the positions I'm going to, and the distance is just the absolute value of the student R minus the destination position row, and then the absolute difference between the student's column and the position column. Put it into my distance array, a vector, sort the distances, and then I add, using the STL command, STL function, accumulate. This will take the first Ti items of this distance array and add them. And this is when you add a bunch of stuff, you have to initialize, right? So if you're trying to add a bunch of stuff in an array, you probably have the in sum equal to 0, and then for int I equal to 0, I less than n, I plus plus, sum plus equals to AI like this. So this is what goes into here, what you initialize your accumulator to. Okay. And then, so this is what the amount of steps you need to bring a faculty into compliance. So in the main loop, I have an array collecting the number of steps for each faculty. But I don't have to bring all the faculties in compliance, only G of them. So I use the same trick. I sort it, and I add the smallest, smallest values, and that's the answer. Okay, there are lots of steps here. I wrote a lot of functions. I even used classes and so on because it helps me organize my code. And this is basically what I wrote my very first submission, except 2 characters. And I missed these 2 characters. I know I'm supposed to do it because I did it correctly in the first one, but I forgot here. And that's what screwed me up in and took me 10 submissions to figure out. Okay, so first, why do I need long, long? Because okay, so everything, all the coordinates are at most 10 to the 9. So if where I have to go, it's at one corner and the student is at the other corner, then the total number of steps could be 2 billion, which is still under a normal integer. But you have a lot of students. If everybody has to walk this far or walk very close to this distance, then that you sum them up, that is going to be bigger than a 32-bit integer. So you have to use long, long. Okay, that I knew right away. And I wrote everything like this. But the problem is accumulate. Accumulate in STL is a template function. It doesn't actually know. It will actually look at this and will say, okay, I put in 0 as a long, long. So I better within the template version in C++, it better instantiate it as the long, long version, and everything is fine. But if the third argument, so whatever it is here, you put 0 like this, then 0 STL, well, C++ again, well, when you just put 0, when you just write any number, it's just to take it as a standard integer, which is 32-bit. And in STL, in actually any template code in C++, you can look at the type of the argument and decide which version of the template function to instantiate. And it says, oh, you gave me an int, so I'm gonna create the int 32-bit integer version the of the template function, which will of course cause overflow everywhere. And that's basically the problem. So I actually know this and I remember this, so I wrote 0LL here. But my first submission, for some reason, I'm not quite sure why, but for some reason, I forgot to put LL down here. And so I got that wrong. And then I spent quite a few submissions not knowing that that was the problem and trying to figure out if I screw up something, I rewrote stuff. And then at the end, I just decided I'm going to not use accumulate and write my own loop. And all of a sudden, everything works. And then I realized, well, and actually, I didn't realize that because I changed a bunch of stuff. I didn't really know exactly which of the changes made it work. So I have to then resubmit stuff, undoing changes until I discovered that it was that I forgot an LL in one of the accumulate at the very beginning. Okay, so this is something that I knew because it has bitten me before, but somehow I only remembered half the time this time. Anyway, so this this set this week. This problem itself, I would say, how do I put it? It's definitely a little bit on the harder side. It's not super hard, but there's a lot of stuff going on, and it takes organization skills, maybe writing functions and so on, to think about what you're actually doing so you don't get all confused. And um, so here, that's why I write a lot of functions to make sure that none of the functions, none of the functions get too long that I can't think about what's actually going on. Right, I break down how to process one faculty at a time, and then here I process each faculty, and so on and so forth. And so that's what I would say when you see problems like this. It's algorithmically slightly more challenging, but not doesn't require anything too out of the ordinary, advanced algorithms and so on, just sorting and adding stuff. But you do have to be careful and organize your code so that you don't screw up on messing things up. Right. So um, it's a good exercise to do problems like this. It helps you develop organization skills, top-down thinking, etc., etc. All those things that you learn in 1620 when you're supposed to break down your problem into smaller chunks. I don't do that all the time, but when I have problems like this, I always do it to keep my head clear of what's actually going on. Okay, so I guess that's for this week. Um, I'll post the video soon, and um, the solutions that's are always on GitHub that you can look at. And then tomorrow there will be another set of 5 problems. All right, see you later.